All right. How's it going, everybody? Today we're going to be going over section 7.1, defining and using sequences and series. Now, one of the biggest things that we're going to have to do for today is recognize, well, what's the difference between a sequence and what's the difference between a series? Now, when we get our word wall, we're going to have it there. But I'm going to give you just a brief little description as to what the difference is between a sequence versus a series. Okay. Now, we can see the first definition right away here. And like I said, we'll make a little brief one later on. Sequences, it says, a sequence is an ordered list of numbers. All right. Easy enough. So I'm going to tell you right now, a sequence, like it says, is a list of numbers. And later on, we're going to learn what a series is, but I'm going to give you a heads up. The difference between a sequence and a series is a sequence is a list of numbers, while a series is the sum of that list of numbers. So that's the biggest difference between the two things, right? They're both dealing with a list of numbers, but in a series, we're actually going to add numbers together. And so that's the biggest difference between them. Now, when we're talking about a sequence, aka a list of numbers, we can have two types. There is a finite sequence, as you can see here. And a finite sequence, it says, is a function that has a limited number of terms. So a limited number of terms, and whose domain is a finite set. For instance, 1, 2, 3, and so forth until you get to your last number, however many numbers they want. But notice how you write a finite sequence. We've seen this type of notation set up with the braces because we're making a list of numbers. And it does say that the values in the range are called the terms of the sequence. So one little note that we're going to add here, of course, a finite sequence, and we have an example right here, is basically a list of numbers that ends. So it actually has an end to it. Now there's a reason why we bring that up, and you'll see it coming up right now. In fact, you know what? Let's jump to it right now. The reason there's a difference between a list that actually ends, versus an infinite sequence. Now, when you're dealing with an infinite sequence, it says it's a function that continues without stopping. So basically, it just goes on forever and ever, and it never ends. And it says, and whose domain is a set of positive integers. And so down below, they're going to give us some examples. So we're going to make a little note here, since we made one up on top, that this is basically a list of numbers. So a list of numbers doesn't end. And by the way, so that we can tell them apart, right, from this to this, a list that never ends, because obviously you're not going to keep writing forever and ever. So it's a list of numbers, doesn't end. So they use this symbol. So they use the symbol, which is dot, dot, dot. It just means something's going on forever and ever. So they're going to start using that symbol more. That's how I'm going to be able to tell them apart from each other. And so that's why, if you notice here, they have a little example for us. When you have a finite sequence, look at this sequence. It has 4 terms in it, 2, 4, 6, 8. And it ended right at the 4th term, which is the number 8. On the other hand, if you look at an infinite sequence, well, with an infinite sequence, it just goes on forever and ever. And that's where we see the dot, dot, dot. So technically, again, there is a difference between the two. And that's what we're looking at here. We're looking at those differences between them. Now, the only last thing I want to mention here with these pictures that we have here above, what you need to understand is when we're talking about the terms of a sequence. So the terms of a sequence, that's what we call my a sub 1, my a sub 2, my a sub 3, a sub 4, and so forth until we get to our last term, if it's a finite sequence. This a sub n can also not just represent the last term. I want to show you down here, a sequence can be specified by an equation or a rule. So for example, both these sequences up here can be written using this rule. They're basically saying this is the pattern that these sequences actually follow. So they're following some sort of pattern, and that's what leads to this list. So sometimes we have a list just like they gave us here. Sometimes we have to create them, and that's actually the first thing we're going to be doing for today. So that's why when we look at example number 1, it says, write the first 6 terms of, and notice how they gave me a rule. This is the rule or an equation, think of it that way, that I'm going to use to find the first 6 terms of this sequence. So here's how we find it. A sub n, again, this represents a formula. And if this is the formula I'm supposed to use, and I want to find a sub 1, well then what they're telling me to do is I'm going to plug in the number 1. So then it's 2 times 1, because that's my term value that I'm finding, plus 5. And when I do the math, well, I get a 7 out of it. Well, let's see. If I do a sub 2, well, then that's 2 times 2, because I'm plugging in a 2 now, into the exact same formula. Notice we have to keep using the same one. They're saying that's how you're going to create your list, and we get a 9. And they said they wanted the first 6, so I'll just keep going. A sub 3, well, then I'm going to plug in a 3. Plus 5 is now 11. Now I'm starting to notice a pattern. And if you notice a pattern, then feel free to start creating this list based on that pattern. Let me see, I'm going to do one more here. A sub 4 would be 2 times 4 plus 5. Well, that's 8 plus 5. And I already knew it was 13 because I see a pattern here. See, if you notice, it's going up by 2. So we see what the pattern is. So now instead of plugging in, if you see a pattern, feel free to just write out the next few numbers. Like I know if this was 13, I'll add a 2. Well, then that's 15. For my a sub 6, because they did want 6 numbers, well, I know that to the 15, I'm just going to add a 2, and there's my 17. And after all of that, I'm officially done. They said, write the first 6 terms using this rule or this equation. So here is my list of numbers. Now, this would be a finite sequence because we're ending it at 6 values. So it's 7, 9, 11, 13, and 17. Again, when you're creating, right, a sequence, you're creating a list of numbers, and this is how we would write it out. Look at that pattern going up by 2. Oh, I missed the 15 there. Just realized. So missing 1, if this thing works. There we go. So 15, I forgot that one, and then the 17. I knew there was something missing. 1, 2, 3, 4, 5, 6. There you go. We needed 6 terms. Now, looking at letter B here, now they gave it to me in the form of a function. Remember, it's a function, an equation. It's still the rule that we're going to be using. So if they want me to find the first 6 terms, then I will plug in a 1. So notice a little bit of a different setup, still the same concept. Then I'm going to go negative 3 to the power of 1 minus 1. Now, obviously, feel free to use decimals on some of these, because technically that's negative 3 to the 0, but anything to the power of 0 is an automatic 1. That's what we learned not too long ago. F of 2 would be next. So that's negative 3 to the power of 2 minus 1. Again, we're just plugging in numbers. But that would be negative 3 to the power of 1, which is negative 3. Well, I don't see a pattern showing up yet, so let's see. F of 3 would be next. So negative 3 to the power of 3 minus 1. So that's negative 3 to the power of 2. All right, so let's see what we get here. That's a positive 9. All right, I still don't see a pattern. Maybe you do already. Let's see. Let's try the fourth one. Negative 3 to the power of 4 minus 1 would be negative 3 to the power of 3. We've seen this one plenty, but now it's negative 27. And I kind of see the pattern. Now, if you don't see the pattern, keep going. You just need 2 more to go. Anyways, let the calculators help you. But I'm already noticing a pattern. Notice 1 times negative 3 would give me negative 3. Negative 3 times negative 3 would give me a positive 9. So you see, I found the pattern. The pattern is that I'm multiplying by negative 3 every single time. So I can continue that And that'll save me a little bit of time, or feel free to plug in. You don't have to see the pattern right away. But negative 27 times negative 3 would actually give me a positive 81 as a result. And f of 6, because yes, they wanted 6 values, f of 6 would be 81 times negative 3 would be negative 243. So remember, it continues. That's the pattern that we found. So that's how we can get our list going a little bit faster. And so now I'm just going to write my list out. So here's my brace. It's 1, comma, negative 3, 9, negative 27, the positive 81, and of course the negative 243. And let me make sure I did get all 6 this time. Yep, there they are. And that's how we create the first 6 terms. Now, I'm going to do one more with you before we pause so that you can try 2 of these out on your own. So we're going to do number 3 here really quick because it's the one that looks a little bit different than the others. So they want the first 6 terms, right? That's all they're doing. They're asking for the first 6 terms. So here we go. A sub 1 is equal to 1 plus 1 plus 1. All right, well, then that's just a half. Notice they never said anything about decimals, no rounding. Then just leave it as a fraction. That's okay to leave it like that. A sub 2 would be 1 over 2 plus 1, so 1 over 3. A sub 3, actually, I just noticed something. That should be a 2 on top. Look at that. There's an n. Then you have to keep changing that number on top. So it's 2 over 3. There we go. All right, I'm using this formula. Put a 3 on the top and a 3 plus 1 at the bottom. Then my answer is 3 over 4. All right, I'm starting to see a pattern. Not that it's an addition pattern or a multiplication, but every time I have to look, if there's a 4 on the top, and of course, no surprise, I'm going to have a 5 at the bottom. See, that's the pattern I'm seeing. 1, 2, 3, 4 on the top, 2, 3, 4, 5. So it's always one bigger. So I already know that 8 to the 5th will be a 5 on the top and a 6 at the bottom because it's one more than what I plugged in. 8 to the 6, of course, would have the 6 on the top and a 7 at the bottom because it's one more than whatever I plugged in. But again, if you don't see a pattern, feel free to type them all in or plug them in. And of course, here's my set for this one. And yes, fractions are fine. 1/2, 2/3, 3 over 4, and 4 over 5. It's 5 over 6. I almost forgot those last two there. 5 over 6 and 6 over 7. This would be my sequence that was created using this formula right here. And that's what these formulas are for, so that we can create these lists. So right now we're going to pause the video so that you can take a moment to work on numbers 1 and 2. So take a moment to try those out and then check your answers. So now we're going to get into the last part of our notes where we're going to be writing rules for series. So we're finally at the series. And remember what we said earlier, a series is just a list of numbers, but we're going to be adding that list of numbers. So we're still going to create lists because I need numbers that I have to actually add. So we're still going to be doing something similar to what we were doing before. So let's start reading through it. When the terms of a sequence are added together, the resulting expression is a series. So there it is. A series is basically a sequence where all the numbers are added together. Okay. So let's see, we can make a little note there. So a series, we're basically going to add a list of numbers. Okay. Notice, of course, that we can add a finite series. Now, this one's a little bit easier to do because when you have a finite series, you have an exact amount of values that we're going to be adding because this list actually ends. So you see, I'd be able to add this, and I would say, oh, my answer is 20 because it actually ended. Now, on the other hand, these are the ones that get a little tricky, right? Because if you have an infinite series and there's a dot, 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 I really can't give an answer yet, especially some of these problems. The numbers might just be getting bigger and bigger, like in this case. Just remember, they go on forever. So you might say, well, then how can you add something that goes on forever? there are specific series that we can actually add, even if they're infinite. But we're not really going to work with those too much. That's for some higher level math that we're thinking there. But they just want to let you know that there are two types. There's a finite and an infinite amount. Now, how do we recognize a series? Now, you saw when we were creating a sequence, they would give me a rule or a formula, and then I would work with it to create my list of numbers. You will recognize a series very easily because they're going to bring in what they call a summation notation. And summation notation, it says, you can use summation notation to write a series. So, for example, the two series above can be written as summation notation as follows. So, check it out. So, here's that finite one we saw earlier, right? Right above, right here. So, there's this finite series. And they're saying this list of numbers can be turned into this. Notice that symbol they're using. They can also do that for the infinite one that we saw above. So here's that same list of numbers. And notice how they're using the same symbol when you're setting up an infinite one. Now, there's a couple of little details here that are going to help me, of course. Notice this one had a sub 1, a sub 2, a sub 3, a sub 4. So I'm going to use this one here to guide me. A sub 1, a sub 2, a sub 3, a sub 4. Notice this bottom value. It says the number 1. Well, that's because that's the first term. And so in order for you to find that first term, all you have to do is plug it into that formula. So that's the very first number that you're going to plug in. So it's the first number you plug in. And then, of course, when I look up here, it's the number 4. Well, surprise, surprise, this one had 4 terms. That's basically the last term. It's the last number you plug in. So they're letting you know how many numbers are going to be in your sequence that eventually you're going to add up. And if you notice right in between, right here, there's the rule. This is our formula or our equation, whatever you want to call it. It's the formula, aka our a sub n. That's what you plug into. And it's what we've been doing. Now, they do use a very special symbol here. And of course, we use a lot of Greek letters in higher levels of math. And so the Greek letter that's being used as our summation notation is called sigma. So a sigma notation, it's kind of a weird looking E, right? It looks like an E there. But that's the symbol. As soon as you see it, we know, boom, this is a series because of this symbol. And then I create my list of numbers, and then I'll be able to add them together. And so there's a couple things that they describe here. They say the index of summation is I and the lower limit. So here's my lower limit. Here's the upper limit. Again, that's where you start. That's where you finish. Sigma notation, there it is, using the Greek letter sigma, stuff we talked about already. Now, what we do want to mention from down here, right before we get to our example, is it says the index of summation for a series does not have to be I, so they can use any letter they want down there. Also, the index does not have to begin at the number 1. So the mistake people make is they go, oh, so I always plug in a 1. You look at the bottom. That's where you're going to start. And so, for instance, if you look at this next problem here that we're about to do, look at where they want you to start. They want you to start at the number 4. And that's okay. That's why we always look before. Before we start, look at the bottom and look at the top. So notice, I'm going to need a sub 4 to begin with. Plus, remember, this is a series. I'll need a sub 5. Plus, I'll need a sub 6. Plus, I'll need a sub 7. And if you're wondering, well, when am I going to stop? Remember, that's what the top number tells me. I know I'm going to end when it says a sub 8. But I have to find this list of numbers because if I don't have them, then what am I going to be adding together? So you see, I have everything ready to go. All I need to do is find my numbers. Well, I'm going to find them the same way I did earlier. The rule hasn't changed. See, here's my formula. My a sub n is right here. That's what I'm going to plug into. A sub n is basically 3 plus, well, I guess I should call it a sub k. That's really what I should be calling it, is k, 3 plus k squared. So here we go. They want me to find a sub 4. All right, well, that's 3 plus 4 squared. Well, 3 plus 4 squared, 4 squared is 16. So 3 plus 16, there it is, 19. 19 is my very first number that I'm going to throw in there. All right, we still have a few to go here. And again, if you notice a pattern, you can fill that out a little bit faster. All right, a sub 5. 3 plus 5 squared. Well, 5 squared is 25. 25 plus 3, 28. There's my next number, 28. And we just have to keep it going. So we're going to keep this one going. We still have to find 3 more. A sub 6 is equal to 3 plus 6 to the power of 2. Well, we know 6 times 6 is 36. So if I add 3, that's 39. So there's my 6th term, or a sub 6 at least. All right, let's keep it going here. A sub 7 is next. So 3 plus 7 squared. We're looking at 3 plus 49. So yeah, we're looking at 52 for this one. So 52. And we still have one more to go. One last one. A sub 8, which is equal to 3 plus 8 squared. Well, 8 squared is 64. 64 plus 3 would be 67. And there's our last value for a sub 8. And yes, when you think, okay, finally, right? Well, we still need the sum, right? We need a total of all these numbers put together. So when I add in the calculator the 19, the 28, 39, 52, 67, I got a grand total of 205. So that's what we're looking for, right? We're looking for that value based off of the list that we just created. Now, I'll do one more, and then that way you can try the last one there on your own. And this will be the end of the notes for this section. But look, here we go again. Now, this time they do want me to start at 1. Okay. So then I know I need a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and that's where I ended. Why do I end it at 5? Because they said stop it at 5, start it at 1. So we know this is a sub 1, and the last one is a sub 5. And so here comes my list. Now, this one's a little bit easier than the one we just did earlier. So let's see. Look at my a sub n. My formula is just, I guess I should call it a sub I. There we go. Is 8i. They keep changing the letter, and that's fine. So a sub 1 is 8 times 1. All right, we're just plugging in for the letter. All right, so here you go, 8. A sub 2. Well, that's just 8 times 2. So 16. A sub 3. Well, that's just 8 times 3. So 24. A sub 4 is just 8 times 4. So if you notice, it's just the multiples of 8, basically. So 32. And finally, of course, we have a sub 5, which I think you should already know it's going to be 40. But we'll make it official there and show the steps. So 40. And now, of course, all I have to do is just add up all these numbers very carefully, and I'll get a grand total of 120. And that's what a series is. A series is me creating a list of numbers, and then at the end, adding them all up. So hopefully this wasn't too difficult for you. But make sure you're going to try number 9. And as soon as you're done with number 9 and you check your answer, then start that classwork. And of course, if you can get to the homework, get that done as well. Have a wonderful day, everybody.